So, morning everybody. Usual story, laptop shut. I won't ask you for your name tags because if I don't know your name by now, I'm not going to know it. Actually, get your name tags out anyway. It helps, right? And let me begin with a question. Now, this is stuff going back to way back when, right? And Pokemon number 1, Quentin, this is yours. I have a multi-class classifier. This is my network. And it outputs P of class given X for every class, right? And then you have your target class, we can call this C prime. What is the cross entropy loss between the two?
It's like the difference between the distribution of your prediction versus.
Yeah, but what is the formula for it?
Oh, let's see. So your prediction minus the. Actually, I'm struggling.
Okay, so here, let me help you, right? This is very entirely logical. One of these guys is your target class, correct? C prime. What do you want to do to the target class? Do you want to increase its probability or lower its probability? Increase it, right? So what would be a reasonable loss? Just increase it, right? The target probability itself is what you want to increase. There is nothing to decrease. There's no comparison per se, right? These are probabilities. And so you want to maximize. And we usually take a log because you want to expand the little things out and not just focus on the large values, right? So it would be maximizing log of P of C prime given X, your parameters. This is what you're going to be maximizing. What would you minimize? 1 minus, the 1 doesn't really matter, right? So this is actually 1 minus, should be, what you end up doing is minimizing minus log of P of C prime given X semicolon theta. This is your negative log probability. Make sense? Right. You don't have to think hard about it. We've gone through this a few times. I know I've thrown formulae at it, but then at the end of the day, you want your classifier to be certain about the correct class. That's it, right? So, and because these are probabilities, if you increase the probability of the correct class, what happens to the incorrect classes? They have to decrease because, when you increase, the probabilities are getting sucked up from one another, right? So you basically, this is it. This is your cross entropy loss. You are maximizing the probability of the correct class, period, right? And consequently, what is the derivative of your loss with respect to the output? So let me call this output y. Y actually represents an entire probability distribution, correct? What is the derivative of the loss with respect to y? What is it going to look like? 1 over? So because this is a log, right? Minus log. What is the derivative of this log? This is y. This whole thing is y, correct? It's y of C prime. So what is the derivative of the loss with respect to the output of the network? The output of the network. So minus 1. But then is this just a single number or a vector? Y is a vector of probabilities, is it not? So what will the derivative be? A single number or a vector? Vector. Okay, so this is a vector. And what is that vector going to look like? Is it a row vector or a column vector, assuming that my output is a column vector? Guys, my output is a column vector, right? This loss is a scalar. What is the shape of the derivative of the loss with respect to my output? It's going to be a, remember, the derivative times, delta y has got to be a scalar, right? Y is a scalar, delta y is a scalar, so the derivative has got to be a row vector, right? And then, okay, what is this? What is this derivative going to be? So let's say my target, I have 4 classes over here. My target class is the second class. Is the loss a function of the output of the first class? Is it? Is it? Where's the first class figuring over here? Is it there at all in this one? Does this say for Pokemon 2, is the first class figuring out here? Okay, so what is the derivative of the loss with respect to the? So this is going to be 0 for the first class, right? It doesn't figure over here. 0 for the third and 0 for the fourth. They all don't figure in the loss. The only term that figures is, so it's going to be the specific term that, yeah, so, and it's going to be what? 1 over P of C prime, right, given x. But don't forget the minus, because there's a negative loss, right? Negative log likelihood. You're minimizing. And it's literally telling you that anytime the derivative is negative, are you trying to increase that value or decrease it? The derivative is negative. The function is going down as you increase it, right? This is a loss. It's telling you to increase the value, right? So this derivative is literally telling you that the correct thing to do is to always be increasing the probability of the correct class, right? Pokemons, that makes sense. Okay, so is this making sense to all of you guys? Guys on Zoom, did that make sense to you? Is there anybody?
Yes.
Okay. Now this is very important, again, that derivative of the loss with respect to the target is going to be a vector of zeros with just a term, which is non-zero, and that one term is going to be minus of 1 over the probability assigned to that class by the network, right? Very simple. Now, I'm going to expand this to attendance pool is 1067, so you can see it. Now, suppose I have a time series, right? And so I have a time series, I have a network, which is and it's outputting something. So this is y0. These are all vectors. At each time, it's outputting a probability distribution over all of the classes, right? This is a time series. And now if I tell you that the target sequence is, C0, C3, C1, C7. So I want the output to be C0 at the first time, C3 at the second time, C1 at the third time, C7 at the fourth time. Okay? What would the loss be between this sequence of outputs and the sequence of classes? Yes, you guys, Joshua, Colton, what would the loss be?
Would he take like a singular loss for each output with respect to its target?
Keep talking.
So, like in that case, you'd have some like the zero vector except for the one target class for each output.
Yeah, so you're going to be summing over time, correct?
Yeah.
You're going to be summing over time because all of these are contributing to the loss. And at each time, you're going to be computing this loss, which is going to give you, there's always a minus, and there's a log, and this is going to be y t of ct, meaning whatever the target class was at time t, computed, read off the probability distribution output at time t. Again, did this make sense? Yes, Chetan.
That would have the property as like as you go more in time, the loss is the value of the loss is smaller, or like
It's going to get larger because it's a negative log, right? It's going to.
But the derivative is smaller because it doesn't change much from the previous.
We can't really make any statements about the derivative. The only thing we're saying right now is that first, we agreed on this principle, did we not? So we agreed on this guy, that this term here, the negative of the log is a loss. If you're making one prediction and there's one class. This we agreed on, right? If we did, just raise your hands. So I know. I'm waiting for you guys to raise your hands, right? And some of you didn't. Why didn't you agree on that?
Because we understand.
So Tom, did you agree? Okay, raise your hands when I ask you to. Otherwise I'll come and ask you, right? So given this, when I just expand it out and say that instead of having a single instance, I have an entire sequence, then it's basically just the sum of the losses at each time because there's a target class at each time, right? And so that's simply going to be the sum over time of the negative of the log of the probability assigned to the target class at each time by the network.
I have a question.
Yes.
The two equations, they just seem to be a negation of the other. I don't know if that was the intention. Because one is for the two equations you showed, the one just seems to be a negation of the other. Was that the intention?
So down here, one was a maximization, the other is a minimization of the negation. Did that answer your question?
Yeah, but you said the first one was for the target class and the second one was for the other classes. So, but I don't see that
This is also for
distinction.
the target class. This is always for the target class. I just negated this instead of, when I want to maximize this log probability, I minimize the negative log.
Okay.
Both are C prime, right? That's all I'm doing. There's nothing particularly sophisticated going on. Everyone with me? Okay. Of the 270 students in class, today we have something like 100 people in class. So post last classes, poll attendance in this classes as well, yes.
So is the loss just the sum, the negative sum of all of the probabilities assigned in each time instance?
Yeah, that's it.
Just that
That's about it, right? So the loss is just the negative sum of the log probabilities assigned at each time. So far so good. Everybody with me? Okay. So I'm going to sort of, why on earth? Okay. I'm not going to, so this was the problem that we were speaking of in the last class. You have order aligned predictions, but which are not time synchronous. We have to figure out how to make these order aligned predictions. And the first question was, how do we perform inference on such a data, right? And then how do we train such models? And for inference, we just looked at a solution. We'll look at other kinds of solutions, right? Partially addressed. And we were looking at how do we train such models. And specifically, we saw that if we were given the time stamps of each output, then you're simply going to be computing the negative log probabilities of the target classes, B, E, F, and E, right, in this case. And that sum of those 4 negative log probabilities is going to be your loss. But then, when you do so, what is happening is that you're ignoring all of the intermediate outputs which also carry valuable information. And so we repeated the labels. And now what we have done is taken something that was intermittent and converted it to a full sequence where you have an output for every time, right? And so as a result, you're going to have a target class at every time, right? And your loss is just the sum of the log probabilities assigned to the target class at each time. Everyone with me? Okay. But the real problem was this, and so when you compute the derivative of the loss, then the derivative of the loss with respect to the output at any time, this is at any particular time, the derivative of the loss is just the vector of zeros except -1 over the probability assigned to the target class at that time. With me? Okay. The problem was no alignment was given, right? And so what we did was we guessed it. We started off with an initial estimate for the model. The initial estimate for the model allowed you to align the inputs to the compressed sequence to the input. And what was the algorithm we used for it? The Viterbi algorithm. I did a really bad job of explaining it in, day before yesterday, but that's my excuse is that I hadn't slept. But anyway, I can go over it again over Piazza if you want, but it's not particularly key. What we're going to talk about today is more important. The Viterbi algorithm is easy enough to understand on your own. So the idea was you guessed an initial alignment, then you trained the models with it, and then you updated your models, and then you guessed an alignment again, right? You could do this in any which way. Here's your first part. Okay, 5 seconds, guys. All right, time's up. Pokemon shift tree, what's the answer to the first one?
I think it's true.
It explicitly estimates the alignment of each training instance and computes the divergence of the estimated alignment. True or false?
True.
True, yes. Yeah, I'm asking the rest of the people in class. True or false? True, right. Second. Okay, Pokemon slacking. What is the answer to the second one? Slacking, slicking. Sungju O. Absent, okay. Pokemon Ivysaur. What's the answer to the second one? Ivysaur. Absent, okay. Pokemon Skeptile.
True.
True? Okay. The second one, is that true or false, guys? True? Okay, perfect. So here you go. It requires re-estimation of the alignments every iteration. Perfect. Now, the problem we saw with this approach was that it really depended on the initial guess. If your initial model was crappy, you're going to start off with a crappy alignment. You're going to learn rubbish, and then you're going to keep sort of building on rubbish. And although in principle you will end up at a local minimum, that local minimum might be really bad, right? So what was the alternative to this? The alternative was, instead of guessing the alignment, let me not take any guess as to pick a particular alignment. Let me consider them all. That way, even if your model is bad and leads you to improper alignments, you are still going to be giving some weight to the correct alignment, however small that might be, and that's going to drag you towards the correct solution, right? And so, again, recap, here's what we did. If you had a symbol sequence, beefy, then you reconstituted a probability table for the target sequence by pulling out the corresponding rows from the output of the network and them up on top like so. And any path from the top left corner of this table to the bottom right corner of the table was a valid alignment of the input of the target sequence to the input, right? And for any given alignment, when you chose the most likely alignment, the most likely alignment ended up giving you a target symbol sequence. So it ended up giving you a target symbol sequence. And so the loss that you computed was merely the sum of the negative sum of the log probabilities of the symbols on the target symbol sequence, right? This is what you were minimizing. And what we did for the Viterbi training was that you committed to the single best alignment. You had a current model, but the current model was crappy. And based on the current model, you picked the most likely alignment, and then you committed to it, and then you updated your model to it. But then here's a different way of looking at it. And the different way of looking at it is like so. I have in my graph, right, I have, say, something of this kind, right? I have a bunch of symbols. And if I began from here and ended here, every path is a valid alignment of the input, right? And how many paths exist? If I go through this graph, right, there's this path, this is path 1, this is path 2, this is path 3, this is path 4, this is path 5, this is path 6, this is path 7. I think there are 7 in this little graph, right? So what I really have is a probability distribution over all 7 paths through the graph. And what I did was to choose the most probable alignment, right? And so I had these 7 paths, and corresponding to each of the 7 paths, there was a probability, and I chose the most likely path. And corresponding to this most likely path, there was a loss, L7, right, which aligns the symbol sequence on this most likely path to the input. But had I chosen this other path, I would have had a different loss, L6. Had I chosen this one, I'd have had a different loss, L5. Had I chosen this one, I would have had a different loss, L1, right? Let's consider all of them. What I'm going, instead of just picking this one guy and choosing the corresponding loss, what I'm going to do is to say, I'm going to take L7 times this probability, plus L6 times this probability, plus L5 times this probability, and just combine all losses with their corresponding weightings. Make sense to everybody? So I'm not committing to any one. I'm just considering more probable losses more, and less probable, more probable alignments more, and less probable alignments less. Yeah.
Where are you like getting the probability for the losses from?
Okay, that's the rest of the class. Okay. And so instead of only selecting the most likely alignment, we are taking an expectation over all possible alignments. But what is the problem with doing that in that explicit manner? That's not the problem. There's something more, right? There's a computational problem. What is that? You're going to have a very large number of alignments. You're going to have to consider them all. So clearly, explicitly taking that expectation does not make sense, right? This is where we do a little bit of mathematical manipulation. And this goes back to the fact that the loss for any given alignment is the sum over time of the negative log of the probabilities of the symbols in the alignment, right? So I have an expectation of a sum, but an expectation is a linear operator. So the expectation of a sum, okay, hang on. The point. Okay, 5 seconds to go. And the Pokemon coming up is Pokemon Electabuzz. So Pokemon Electabuzz, what's the answer to the first question? Electabuzz. Okay, the polls are not posted. Okay. So does somebody else want to answer that first question? True, okay. Electabuzz is missing. Pokemon Pinnacle, Jaime. Second question. Pokemon Pinnacle, also absent, okay. Pokemon Spearow, What's the answer to the second question? Yunjin Na? Absent. Okay. Pokemon Abra. Jiyun Park. What's the answer to the second question?
False.
False. Okay. So the training without alignment computes the average divergence over all possible alignments. It does not require explicit alignment because you're considering every possible alignment, right? Now let's go back to this thing. How do you actually deal with the issue of the computational explosion? And that has to do with this. The probability, the loss for any alignment is simply the negative sum of the log probabilities of the classes on the alignment, right? The expectation of a sum is the sum of an expectation. And so I can kick this expectation operator into the sum, at which point it becomes a sum over time of the expected loss at that time. And so this becomes very beautiful. What I'm doing now is to sum over time like so. And at each time I'm saying, had this symbol, now I'm going to say, this is ba, this is e, right, this is fa, correct? And so I'd say, had this guy been the correct symbol over here, what would the loss have been, right? Had this guy been the correct symbol, what would the loss have been? Had this guy been the correct symbol, what would the loss have been? I'm going to consider the losses for each possibility, and then the total loss at this time is going to be, just the weighted sum. If this were the correct symbol, what is the loss? Multiplied by the probability that this is the correct symbol. Plus, had this been the correct symbol, what is the loss? Multiplied by the probability that it's the correct symbol. Plus, had this been the correct symbol, what is the loss? Multiplied by the probability that it's the correct symbol. And I just do that down the column, and then I go across time. That makes sense, right? We simplified the problem. We didn't actually sum over all of the possible alignments. By rearranging my expectation operator, I just summed over all the nodes in the graph. And it's an strict equivalence. It's exactly the same operation. Make sense, right? And so the problem now really becomes this. How on earth do I compute? It's easy enough. I know what the symbol is. So I know how to compute the loss, right? For this node. Here, it's going to be the negative of the log of the probability assigned to the character B at this point. The thing I have to compute is what is the probability that this was the correct symbol over here. And how do I compute that? So that's also very simple. For example, if I'm looking at that highlighted node over there, then I want to compute the probability that the phoneme E was the correct, in the second position, was the correct phoneme at time, in this case 3, right? What is that? That is going to be the total probability of all paths through the graph that went through the node. Because if that is the correct probability, then every alignment must have gone through that node, right? So the probability that the phoneme E, the first instance of the phoneme E occurred at time 3 in your alignment is the total probability of all paths that went through the corresponding node in the graph. Making sense? Questions on Zoom? Because I'm going to build everything off of this. Zoom, any questions? Yes, Chetan.
So then wouldn't the nodes that are in the center of this table have the highest probabilities because the most paths go through them?
No, but here's the thing. We're going to normalize things. So we're going to make all of these probabilities sum to 1. So it doesn't matter which. If you here, in every column, eventually the probabilities will sum to 1. No single node is going to have more contribution than the others, right? You're looking at it column by column. And we'll see how this works out, right? So the question, again, look at this. Either, this is your complete graph, right? So either this one aligns to the input, or this aligns to the input, or this aligns to the input. So these 3 probabilities must sum to 1. there's no other possibility, correct? And so whatever losses you compute over here, their weights are going to sum to 1. Similarly, at this time, either this one is in the correct alignment, or this one is, or this one is. So those 3 probabilities must sum to 1. So the total probability is always going to sum to 1 at every column. Right? Okay. So how do you compute the probability of this graph? That's easy. That's my graph, right? I'm going to decompose it into 2. I'm going to decompose it into everything that starts from the beginning and ends at that node, and everything that goes from that node out to the end. Okay? And so this is, I'm showing you the math below, but let's skip the math. You can just see this visually. This just makes sense, correct? And so this means that I can, using Bayes' rule, the probability of the graph in pink is going to be the product of the probability of the subgraph in blue times the probability of the subgraph in red conditioned on the subgraph in blue. Right? That's Bayes' rule. If I give you x and y, here x is the probability of the first subgraph, y is the second subgraph. The joint probability of x and y is p of x times p of y given x. Right? Very simple. And now here's where, so this first guy, oh, come on. Something happened. Okay. So now here's where we actually begin take into consideration something called conditional independence. And that's this, that I really have this portion of the subgraph over here, right? And this portion of the subgraph, whatever. I'm bad at drawing things. But then I'm trying to condition this guy on this one. But these probabilities are only dependent on the node probabilities within the graph, correct? When I'm computing node probabilities over here, am I explicitly considering these node probabilities? The answer is no. Why? Because if I go back and look at my network is a recurrent network, right? I have some hidden states, and from this hidden state, there's some additional computation going on, which gives me the probability distribution out here, right? So, but this hidden state is the only thing that influences this guy. These probabilities do not, right? Whatever comes out here does not. And so the probability y1 that I compute is not dependent, has no information about the probability y0, correct? The only way that my probabilities here would influence this probability is if I sample something from here and put it back in. Because what I compute at time 0 is now going to influence what I compute at time 1. But if I'm not doing that, right? If I'm just looking at the computation like so, then the hidden state is directly dependent on the x, and the y's are dependent on the hidden state, right? The y's are not dependent on one another. There is no row, there's no dependence from y0 to y1 when I draw the dependency graph. That making sense to all of you? So which means that conditioned on the input, if I give you x, y0 is independent of y1. If I didn't give you x, they are not, because I don't know what the input is. So from y0, I'm going to have to infer something about h, and then I'm going to have to infer something about y1. But I've given you x, so I know h. Once I know h, y0 and y1 just don't directly affect or influence one another, right? So these are conditionally independent. What this means is that the red graph and the blue graph do not, the probabilities of the red and the blue graph do not affect one another. That makes sense? Right? And so if I'm computing the probability of, so this graph I'm going to call the forward graph, the pink one. This graph I'm going to call the backward graph for reasons that will become apparent in a bit, okay? And so I'm going to call the total probability of the red graph, which ends at phoneme E at time 3, as alpha 3E, or more generally, The subgraph that ends on the rth row at time t is going to be called, the probability of the subgraph is going to be called alpha TR, right? And the probability of the subgraph that begins from the rth row at time t is going to be called beta TR. And the total probability of the entire graph is going to be alpha TR times beta TR. Make sense to everybody? Zoom, any questions? Zoom, questions? No. Okay.
How do you find that middle point? What's so special about the middle point?
No, that's just that there's nothing special about the middle point. We're going to be computing that for every point. I just chose an arbitrary point, right? So again, remember here, when I was computing the loss, I was going across time. At each time, I was going through all the nodes. And then I was computing the average loss, which is the probability of this node times the loss, if that node was on the correct alignment, plus the probability of this node times the loss, if that node were in the correct alignment, and so on. So I was summing things up, right? Which means I needed to know the probability of this node. And so I just chose an arbitrary node, but you're going to have to compute the probability of every single node in your graph. Did that answer your question?
Yeah.
Okay, so nothing special, just some arbitrary TR. Okay, so now,
Question?
yeah,
Yeah, can go back. So I just want to know what is the probability space we're talking about here. I'm confused. If all the probability space is like the path that's from the top left to the bottom right, then
correct.
then any path that goes through in the middle point from left would imply that so I mean, if that's the case, then if the path goes through the middle point, then whatever path goes through in the like in the blue range doesn't matter, right? Because then
It does not matter. You're absolutely right, right? All you're interested in is it's a total probability, correct? The specific path doesn't matter. You want the total probability of all paths through the blue range. All you know is that if you're going through that middle point, you must go through the blue range, right?
yes.
Okay, so you want the total probability of all paths in the blue patch.
But I mean, isn't that going to be 1?
It's not 1, right? It's, again, if I choose this guy here, let's go back to this graph. What is the probability of this node being in the correct alignment? That is going to be the total probability of all paths that go through this node, right? But there are other paths which go through other nodes. Aren't there?
Yes.
Yeah. So if I told you that, if I gave you the information that yes, the correct path did go through this guy, then you're taking that as a given. If you take that as a given, yes, the probabilities of the total, everything in the blue path is going to be, it's conditioned. It has to go through that. It would be 1. But no, we are trying to compute the probability that it went through E. Okay? So bear with me. So let's see how we can compute the total probability of the first subgraph. That's the total subgraph, the subgraph that went through the node E at time 3. Okay? And how can I compute this? It's the probability of all paths that started at the top left and ended up at 3E. That's alpha 3E, right? That's alpha TR, okay? Now, I know that every single path that ended up in the blue graph must either have come through the red node or through the green node, because it has only 2 parents, correct? So it means that the total probability of all paths that end up here is going to be the total probability of all paths that end up at the red node times the probability x times y3e, because it's all paths that end up here and get extended by 1 step, plus the total probability of all paths that end up here and get extended by 1 step. That making sense to you guys? Zoom? Questions? No, okay. So now the total probability of all paths that end up at 3e, I'm calling that alpha 3e, okay? What is the total probability of all paths that end up at 2b? So Pokemon Articuno, what would that be? Pokemon Articuno?
Can you hear me?
Yes.
Not
So
sure.
again, to repeat, the total probability of all paths that end up at 3e, I'm calling that alpha 3e, right? So what is the total probability of all paths that end up at 2b? What would that be? Okay, somebody else? Someone want to help him?
Alpha to B.
That's going to be just alpha 2b, right? Similarly, what is the total probability of all paths that end up at 2e? Alpha 2e, correct? And so this means that alpha 3e is going to be alpha 2b times y3e plus alpha 2e times y3e. That makes sense to you guys? Right? Very simple. There's nothing particularly complicated about this, which generalizes to saying that alpha tr is going to be the sum over all parents, all nodes that can lead to alpha tr, right? Of the alpha, and those are going to be at time t minus 1 of alpha t minus 1 parent. So this y in fact can come outside, right? It's the total alpha of all the parents multiplied by y3e. That makes sense to you guys? Guys on Zoom, that makes sense?
Yes.
Yeah.
Beautiful, right? Very simple. And so here's how I can do this. I can compute this alpha. Now that you know how this happens, I can compute this alpha for every single node in the graph. And this is how I would do it. So the alpha tr is the sum over all parents of tr of the alphas for the parent times by tsr, right? So simple. So again, observe that in this case, you're summing the alphas at the previous time for all the nodes that can lead to the current node. And then you're multiplying that sum with the probability at the current node, okay? So let me go back and show you how this whole thing is done. There's an algorithm on the slide, but let's just do this with pictures. Let's consider time 1. At time 1, there's only one node that's allowed, right? And that's going to be the top left node. The rest of the nodes are not permitted, which means that the total probability of the alpha is going to be y0b at the top left corner, and the rest of them are going to be zeros because the rest of them are just not allowed, right? Make sense? And so you can just assign the alphas at the first time. Then I can take a step forward, and then I can just simply use this formula where for every node, I just go down this column. And for every node in the column, I sum up the alphas for the parents and then multiply that by the node probability, right? And so now I've computed the alphas for the second time. And then I can take a step forward again, and then I can go down the column. And for every node in the column, I can sum up the alphas for the parents of the node and then multiply that by the node probability. In this case, there are only 2 parents. There will be other situations where there will be more parents, right? We'll see that also. And then I can move on, right? And so I can keep computing this till I compute the alphas for every node in the graph, right? Is this making sense to you guys? The pseudocode, I'm not going over code because code. Do you mind shutting your laptop? If you really need to work on your laptop, guys, go outside, finish your work, come back in. Okay? I do not want to have to repeat this again in every class. All right. So I have some pseudocode. And I don't really need to go through it. I'm sure you can figure it out. Basically, we are going from left to right. At time 0, we've just assigned the alpha to the top left node. The rest of the nodes have alpha 0. Then I'm just going through time. At each time, I'm going down the columns go down the column, and at each node, I'm just summing up the alphas for the parents and multiplying it by the node probability, right? Easy. And I'm done. This is a very simple algorithm. And the number of computations I'm going to do in the worst case is going to be t times n squared, whereas the n is the number of rows in the table.
A question, please.
Yeah.
Yeah, what we really need is the alpha 8y.
There's something, I can't hear you. Can you repeat yourself? There was an echo. Could you please repeat that?
I said that what we really want is alpha 8y.
So,
But why are we computing all the alpha? I mean, if you just want alpha 8y, why not do recursive algorithm doing,
we
from
don't
alpha
want
8y?
we don't want just alpha 8y. We want alphas for every single node. Why? Because remember, in my example, I was literally looking for the alpha at 3e, correct? So what we are trying to do is we want, so going back to my graph out here, for every single node in the graph, you're going to compute the total probability of all paths going through that node, right? And that total probability has two terms, the alpha and the beta. So which means that you need the alphas for every node in the graph.
Okay, sorry, thank you.
Right? And similarly, I need the betas for it. And so that's my so-called forward algorithm, which allows me to compute things all the way to the end. And alpha 8e is the total probability of all paths that ended up at e at time 8, which is going to be the total probability of all alignments of BFE to the input. That's the probability of BFE, basically, right? All right, anyway. Now, here's the other thing. Now, the second portion that I need, so the first time I'm going to call this the forward probability alpha TR. I know how to compute it for every single node in the graph. In one pass through the graph, I'm going to compute everything. I'm done, okay? Now I need to know the second term. How am I going to compute the backward probability, which is the probability of the blue subgraph? Okay. Now, how would you do this if I asked you to do it? Similar to the way we did the forward, but there's a small difference, right? That node was part of the graph going forward. It's not part of the graph going backward, and this can make things a little complex, right? So here's what I'm going to do. I'm going to just include the node in the graph. So that's if I include the node in the graph, that's going to be the total probability of all paths starting from that node till the end. And then once I've computed that probability, I can divide by the probability of the node in the graph and get rid of it. Right? So this is a computational efficiency thing, right? If I include this, then I can compute the total probability of all paths from that node to the end, and I divide it out. No biggie, right? And once I do so, then I can compute the probability of all paths starting from y3e till the end of the graph. That I'm calling beta 3e, okay? Now let's look at what happens here. Any path going from y3e to the end must either go through y4e or through y4f. Only two possibilities, correct? What is, now again, the probability of all paths from y3e to the end, I'm calling this beta 3e, right? Now beta 3e, using the same logic, is going to be y3e times the probability of all paths from here to the end plus y3e times the probability of all paths from here to the end. Make sense? Right. Okay, so Pokemon Geodude, what is the total probability of all paths from here to the end? Geodude, what's that?
Yes, I'm here, but
Pardon me, can you say that aloud, please?
oh, I don't know well, sorry.
Anybody want to help him? Yeah, that's this guy over here is simply going to be, again, the probability of all paths from any node to the end is the beta at that node, correct? That's simply going to be beta 4e, right? What about this one? The total probability of all paths from y4f to the end. Pokemon Exploud, what is that? Yishuan Yin. What is that? Absent?
Yeah.
Yeah, go
Can
ahead.
you repeat the question?
So what is the total probability of all paths starting from this red node y4f to the end?
Y4, what IF and then it's Y5F plus Y5 I1?
No, but in terms of the notation we just said, right? Because we just said that the total probability of all paths from y3e to the end was beta 3e. So beta 3e, we agree, is going to be the y3e times the total probability of all paths from here to the end, plus y3e times the total probability of all paths from here to the end, right? So what is this guy over here? What is the total probability of all paths from here to the end in terms of betas?
It's beta 4F.
Beta 4f, right? And therefore, I can just write that beta 3e is going to be y3e times beta 3e plus, sorry, this should have been beta 4e. Let's note this down, plus beta 4f, right? So that makes sense? And that's easy, right? And so this gives us our algorithm. The beta hat, which is including the node, is for at any time is the probability, basically the probability of that node itself, right? Times the sum over all of its successors of the betas for the successors. Make sense? Right. And so this gives us our nice little algorithm. I'm going to start from the end, and I know that the bottom right node is the only valid node. So the beta for the bottom right node is simply going to be y8e. The rest of the betas are going to be 0. Okay? And then I've filled up those betas, I take a step back, and then I go up the column, and for every entry in the column, I'm going to compute the betas as simply the probability of that node itself times the betas for all of its children. So I've computed the betas for that guy. Then I take a step back, and then I compute the betas for all the nodes in the column here and all the nodes in the column here. And so at each time, all I'm doing now, observe that I'm going backwards from the end, which is why we call it the backward probability. At the very end, the beta for this node is y8e. The rest of the betas are set to 0. Then I keep going backwards in time at each point to compute the beta for any node. I'm going to compute the beta for all the nodes in that column. And the beta for any node is going to be the probability in the node plus the sums of the betas for all of its children. Very trivial, right? I don't need to give you code. You guys can write code. The visuals tell you exactly what to do. And so once I'm done, I'm going to have the betas for all of the nodes in the graph, right? I have the betas and alphas for everything now. I've done the forward algorithm. I've done the backward algorithm. But the betas, the way I computed it, I actually factored in the node probability. But I didn't want the node probability to be part of the computation, right? We just included the node because it was convenient. It gave us a simple algorithm to compute things backwards. But once you've computed the betas, you can divide by the node probability itself to get rid of the excess node probability, right? Again, the reason we are doing this final division was what we really wanted was this guy with not including the node, but then we added the node just to make computation more convenient. And so then you're going to have to divide by the node probability to get rid of it. That's it. And so that gave us this. This gave us the beta hats. I divide by the node probability. Now I have the betas for everything, right? Easy? Yes.
So just to verify, by adding that Y3 node, that's how we factor in the node in the
Backward, yeah.
backward, but then we just take that out so that we don't.
We don't double compute it. Yeah, that's it, right, yeah.
If you're calculating beta by saying that it's the sum of the beta of the children, then how are we computing it backwards from 80?
Yeah, because the children are always ahead of you, so you have to start from the end and go backwards. You can't go forward because you don't have the betas for the things in future, right?
Yeah, but we have the beta for the last one.
So you start off with the beta at the very end, and then you're going backwards because the children are always ahead of you.
Okay.
Right? Yeah. And so we have computed the probability of the blue graph. We have the alpha and the beta. And now the probability of all paths that go through the node is simply the product of the alpha and the beta. But it's proportional to the product of the alpha and the beta. It's not actually the product of the alpha and the beta. Why? Because if you look at the probabilities of the alphas and betas and you multiply the two, you got these terms and then sum them up over the column. Will they sum to 1? No, right? Because as we said, alpha 8e is actually the probability of B phi as computed by the graph, right? So what we really need to do to convert this to a probability is you go down the column, you multiply alpha and beta, and then you divide by the sum of the alpha beta products down the column. And so here's what you would get. Once you've done the forward pass and the backward pass, you would have the alpha, beta, and betas for every node in the graph. So you're going to multiply the alpha and beta here, the alpha and beta here, the alpha and beta here. You're going to get 3 terms. Then you sum them up and normalize so that now those things end up being equal to 1, right? Summing to 1. And I'm going to call that gamma. That's a gamma TR. Right? So computing these gammas, this gamma is now the probability that if this input corresponds to B phi, it gives me the probability that the rth symbol aligned at time t. Right? And so now that I have the gammas, I can go back and compute my loss, which is simply I'm summing over all the nodes in the graph. I'm going from left to right, summing over time, then summing over all the columns and all the rows in the column, and I'm multiplying the loss of the node, which is simply the negative log probability at the node, as we saw early on, by the corresponding gamma, right? And summing this up. This is a very simple operation, and so this is trivial. We can, once you compute it, you can take the derivatives. Here's a okay, time's up. Pokemon Ponita, what's the answer? Is the first statement true? Janet, is that first statement true?
Yes, it's
Okay, thank you. And Pokemon Puchiana, that's Chetan. Is the second statement true? Also true, okay. And so the forward-backward algorithm is used to compute the a posteriori probability of aligning each symbol in our compressed reduced sequence to the input. And these are required to compute the expected divergence, right, over all possible alignments. But once you've computed the expected divergence, it's very trivial for me to actually compute the derivatives of this expected divergence with respect to the output. So here's what happened. This actually ends up becoming quite complicated. At each time, the network computed probabilities for all symbols in my vocabulary, right? So at each time, I got, maybe from Y0R to Y0Z, all of these were computed. But only some of these probabilities appeared in the graph. So which means that the derivatives for the rest of these guys must be 0, right? They don't appear in the graph. If those changed, they would not change the loss. So all that you need to do, this is at each time, right? You're going to need to, for back propagation through time, you need the derivative of the loss with respect to the output at each time, right? So this is for each time. And then, guys, I'm not going to finish on time today, so I'll probably sort of drag this into the next class because I don't want to inflict another 8 p.m. class on you guys. What that means is that next week's lecture is going to be Wednesday lecture is going to leak onto the week after, right? Anyway, so this, I need this set of all probabilities. The only probabilities that I have are the ones that actually occurred in my label sequence. And so only those probabilities will have derivatives. And the derivative for any particular symbol is simply going to be the derivative of this divergence with respect to the probability assigned to that symbol at that time, right? And those derivatives are simply going to be, again, these are the terms I must compute from my divergence formula. And I know that if I look over here, this is simply the sum. This is at any given time, right? So I only need to sum over all of the columns. I'm going to be summing over all of the columns the derivative of gamma times the log, right? So out here, if I have b phi, right? Let me take a look. If I consider the time 4, right? Time 4. If I want the derivative of the divergence with respect to the output of the network at time 4, then the derivative terms for anything other than b, phi, and e is going to be 0. So those can be discarded. What is the derivative for e? The derivative for e occurs twice in the graph. So the contribution of e to the graph, to the overall loss is going to be gamma 4 e in the first, gamma 4 2 times ye4 plus gamma 4 4 times ye4, right? So it's going to be the gamma over here, up there, times ye4 plus gamma over here times ye4. That's the contribution of e at time 4. And so the derivative of the loss over here is simply going to be the sum of, okay, there are two terms. The derivative of, it's going to be for any particular node, the derivative for that node is going to be gamma divided by y. We already saw that, right? Gamma is just a multiplicative term, plus the derivative of gamma times log y, again. Because for any given node, it's gamma times log y. That's the contribution to the loss, right? And as it turns out, that first term is very trivial. It's just gamma over y. You know exactly how to get it. The derivative of the second term is very ugly because gamma has to consider everything in future and everything in past, and it's a bit nasty. So what we are going to do is to just, when things get too complex, you take an engineering solution. You come up with an alternative mathematical explanation and throw it away. And so we decided the second term is kind of puzzling, can be complicated. So I'm going to say, instead of just trying to train my network to minimize losses in the usual discriminative way, I'm maximizing the likelihood of my data. And if you come up with this alternative explanation, then that second term can be thrown away. And then you're just left with the first term, which is the ratio of the gamma at that node to the probability of the node itself. That's for one node, right? But then if I'm really interested in the symbol, in the symbol y, I have to sum this over all the rows that include, the symbol e. Then I have to sum this over all the rows that include e. And so the derivative of the divergence with respect to the probability assigned to phoneme e at time 4 over here is going to be -1 over the probability, like the usual case, except now we are summing the gammas for all the rows that included e. Now, intuitively, what does that mean? Again, so let's say I had b phi, right? So out here, let's consider this node. You're asking yourself, had b been the correct symbol at this time, what is the probability of, what is the loss? That's simply going to be y of b at time 4, right? But then you want to multiply that by the probability that b was the correct symbol. So what you will do is to go back, go down this column, and find all the rows in which b happened and sum up their gammas, right? So it's going to be negative log probability of b multiplied by the sum of all the gammas for all the rows in which b happened, right? Similarly, it's a negative log probability of e multiplied by the sum of the gammas for all the rows in which e happened, and so on. And so when you compute the derivative, because you're throwing away the second term, it's going to be simply the sum of the gammas divided by the probability of E, right? That's it. That makes sense to everybody? Right. And so here's the overall training procedure. When I'm giving you an order aligned, but otherwise insufficiently informed training instance. I'm going to set up my network, typically a many-layered LSTM, initialize all the parameters of my network. Then using the parameters of my network, I'm going to compute my probabilities, like so, right? And then I'm going to create my alternate table, where I've just pulled up all the corresponding rows and created my secondary table where some rows might be repeated, right? And then from this one, I'm going to perform a forward pass and compute alphas for all the nodes in the table. I perform a backward pass and compute the betas for all the terms in the table. And then from those, I can compute the gammas, right? Which is just the product of the alphas and betas. You normalize it across the column. And then I'm going to compute my divergence derivative for the output of the network at each time, where the entries are simply going to be zeros for all the symbols that didn't occur in my label sequence. And for the symbols that did occur in my label sequence, it's going to be the sum of the gammas divided by, or the negative of the sum of the gammas for the rows in which that symbol occurred, divided by the probability assigned to that symbol, right? And having done that, now I can just backpropagate this to train my network. So questions? Yeah.
I didn't understand how we threw away the second term of the chain rule.
Just like that.
But like, why did we not like?
You could compute it, it gets to be a lot more tedious. So it turns out that it's a perfectly valid mathematical explanation for throwing it away. So we do that.
Is it because we're just working with probabilities that we don't need to consider?
If you think of it as discriminatively training the network, then you need to consider it. If you think of it as maximizing the probability if you're training data, you don't need to consider it. And so we choose the second explanation because it's easier. That's it. Right? Okay, so the story so far, sequence to sequence networks which irregularly output symbols can be decoded, right? Can be aligned using Viterbi decoding. Training can be performed by iteratively estimating the alignment by Viterbi decoding and time synchronous training, right? Or can be performed by optimizing the expected error over all possible alignments, which is what we did. But in all of these, we ignored a very key problem. And that is the business of repeating symbols, right? And that's, consider this. I have a decode. So I chose an alignment. It's RR, R, E, 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 D. Is this the word read or is this the word read? Which one is it? We have no way of knowing, right? So how do you ensure that you can actually distinguish between the two? It's impossible from just this. So we're going to have to introduce a queue. Now observe that when I want to take this alignment and compress it to a reduced sequence, I do this by just eliminating repetitions, right? So I'm going to introduce a symbol which allows me, so this is basically this problem, right? You can't distinguish between repetitions and a single instance. So I'm going to introduce a do nothing symbol. This do nothing symbol literally does nothing. When you're done, it doesn't exist anymore. It's what we will call a blank. It's not a space. It's just a blank. It's a do nothing symbol. We're just calling it a blank, right? And you're going to extend your vocabulary by this one do nothing symbol. And when you compress it, the do nothing symbol will get compressed out and disappear, but then it's going to separate things on either side because it's a unique symbol, right? If I had EEE, YYY, EEE, and you compressed it, it's going to be EYE, right? If I have EEE, blank, 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 EEE, and I compress it, it's going to be E blank E, but then the blank gets thrown out. You end up with two E's. And so the job of the blank symbol is it's just a nothing marker, which ensures that it separates out repetitions. And so I have this blank, right? If I have an alignment which is 3 R's, 3 blanks, 2 E's, 3 blanks, and D's, when I compress it, I get rid of repetitions. The R's go away, the blank become a single blank, but then it's a nothing symbol. It's an invisible symbol. You don't see it. And then you get an E, and then you get an invisible symbol, and then you get a D, so it just becomes red, right? So also this guy, this is going to become an R. The blank is invisible, you won't see it. This becomes an E. The blank is invisible, you won't see it. This becomes an E. This becomes a D. So this becomes read, right? This becomes an R, R, E, D, D, right? As you can see. And this would become, what would this become? It's going to be R, 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 E, E, D, D, D. So you see how the blank works. The blank is just like any other symbol, except when you print it out, you don't print it. It's an invisible symbol. It's a do-nothing symbol, right? And by introducing this do-nothing symbol, I've changed my problem. I've got rid of the problem of ambiguity of repetition. And so, just to ensure that you got it, here's a little code. Okay, Vibha, which is the correct one? Last one. Yeah, that was her Pokemon turn. So, so the last one is the only correct one, right? You got it. So you guys got it. And now what this means is that I'm going to introduce a blank in my vocabulary. But here's the problem. Blanks are invisible, right? So when someone gives you a label sequence, they tell you this is the word Billy, right? They're not sticking blanks in because blanks may or may not happen, right? For example, consider this. This I, blank, blank, LLL, and I, LLL, both are going to just compress to IL. And nobody really bothered to tell you if there was a blank in the middle or not. That information is missing. And so you're going to have to train a model that can predict probabilities for blanks without ever having seen a real blank. Right? Turns out it's possible. It's not hard. And so here's how we're going to do it. Now again, the moment I introduce a blank, notice how repetitions are no longer an issue. So this one is simply going to become beefy, right? On the other hand, if this were my most likely symbol at each time, this is going to become beef. This is also beefy, right? What would this be? Anybody? What would this be? Pokemon Bulbasaur. What would this be? Pokemon Bulbasaur, Geon, absent, okay? Pokemon Charmeleon, Himbaza, what would this be? Charmeleon, also absent. Okay, Pokemon Nosepass, that's Quentin, what would this be? So it's going to be beef, then another F, right? 2 Fs, easy. So now this was, so when I composed the graph, right, for beefy, this was how you composed it in the past. But now I'm going to have to change things. So earlier, here's what we had. Here's how you think about it. And just to make things, ugly, instead of calling it beefy, I'm going to call it, so you had b going to going to f, going to e, right? This was how we defined beefy in the past. Now I'm going to say there can be an initial blank. If there's an initial blank, this must go to B, correct? But then there can be a blank. Then this must go to E, but then B can also directly go to E. You see what I'm doing over here? That I can have a blank between 2 symbols, but the blank is optional. I can go directly from B to E, right? So similar, now suppose the next character is fur, then how would this graph extend? how would this graph extend? The next one is far. What would this be? Right, this is, I erased things, did I not? Okay. So this was, I had an initial blank, then this went to Burr, then there's a blank, this went to E, I'm putting this to indicate the blank, right? E, and, but then I had this possibility as well, right? Then what would the next thing be? What would the next thing be?
The same thing.
Same thing, I have a possible blank, and then I have far, correct? So this was easy. But then now let me take another thing. Suppose I want B, E, E, right? If this is what I need, then again, I can have an initial blank, right? This is optional. Then it's going to go to a B. Then I can have a blank, and this can go to an E. And I can have this. What happens next? I have to have a blank, because if I don't have a blank, things will get compressed, right? And so then here I do not have this skipping connection, because if I did, then it's just going to be, they're going to compress into a single E, right? So that's it. That's the only extra thing that I have to worry about. And so here's what it's going to look like, right? When I think of B Eve. This making sense to everybody? Right. And so this means that if I want to compose a graph for B Eve, I'm going to introduce a blank between every two symbols, but the blank is going to be optional, where the symbols on either side are not repetitions, but mandatory, where the symbols on either side are repetitions. Right. And so when I compose my graph, this is what it's going to look like. I'm going to have the arrows just the same as before. I can also have an empty blank at the end after the final E, right? Or far. And so when I compose my graph, this is what it's going to look like. I'll have all of these edges where, I can from any symbol, I can either go to the blank below it or directly go to the symbol after it, unless those two symbols are the same. This makes sense to everybody, the structure of this graph? So observe over here that in this case, from Burr at any point, I can either go to the blank and from there to E. From Burr, I can either go to the blank and from there to E, or I can go from Burr directly to E, right? But from E, from the first E, I have no way, I can't really skip directly to the second E. From the first E, I must go through the blank. Otherwise, I have no way of separating repetitions. Right? Okay. That's about it, yes.
What about so in the examples there is sentences with multiple lines that follow each other?
So this is an alignment, right? So look at this. The horizontal edge is simply going to become many blanks, which will compress. Right? This is just your standard graph, right? Any path from beginning to end is a valid alignment. Any path from any node in the first column to any valid node in the last column is going to be a valid alignment. That's it, right? And so now this is easy. And I've just observed that especially we have allowed a blank before the first Burr and after the last. And skips are permitted across a blank, but only if the symbols on the either side are different. That's about it. And so here's what the forward algorithm is going to look like. Now I'm going to compute alphas for the first two nodes. And the rest of the alphas are going to be set to 0. Okay? Then I go from left to right as before, except that when I go left to right, I'm summing over all of the parents, and in the two E's, the second E is going to have only 2 parents, but the rest of the nodes will have 3 parents, and that's going to give me alphas going forward to it, beginning to end. And then same thing, when I'm doing my betas, I'm going to be setting my betas for the last 2 nodes in the graph, and then everything else is a 0 beta, and then I can just work my way backwards. And again, I'm summing the betas for the children, and some of the rows will have 3 children, some of the rows will have 2 children. And they're going to have 3 children if the next symbol is not the same. They're going to have only 2 children if the next symbol is the same, right? The blanks will always have, blank rows will always have only 2 children and 2 predecessors, because you cannot skip from a blank to a blank. right? That's about it. Nothing complex. You can actually look through the slides. You can look through the pseudocode, and it should all make sense. And so now here's how you'd set up your training procedure, which is you're going to set up your network, and you're going to include a blank in your vocabulary. And observe that although I have not explicitly represented blanks in my label sequence, I have given you blanks. I just didn't write them. Where did I give you blanks? Anytime there was a repeated symbol, there was an implicit blank between the two. Right? The fact that there are repeated symbols in your training data means that I have given you instances of a blank. I just didn't mark them. Right? And in other cases, it's a skippable blank. And so now I can just set up my network, and then I can perform a forward pass to compute all my forward probabilities. I can compute a backward pass to compute all my backward probabilities, compute my gammas just as before. I compute my derivatives, my derivative loss, and I can use these to train up mine. We'll stop right here. I'm 1 minute over. I apologize, but yes. We will pick up in the next class, but I'm hoping this made sense to everybody, right? Please take a look at the pseudocode for beam search. It will end up in your quiz. Everything on the slides will be on the quiz. I may be covering it in the next class. That doesn't mean it won't be on the quiz. Again, expect everything on the slides in the quiz. Thank you, everybody.